welcome back. In today's video, we are going to talk about a very interesting search algorithm in artificial intelligence called the hill climbing algorithm. Hill climbing algorithm is a local search algorithm that continuously moves towards the best solution. All right, just like how we would climb a hill to reach its peak. For example, there are even mountains. You can not specifically a hill. You can take mountains like K2 as there are multiple routes to reach the summit. Like that, this algorithm works by you know continuously moving towards the best path or best solution. We'll walk through the basic concept, understand how local and global heuristics works, and then I'll show you even an example using an actual problem that we solved using this algorithm. So let's start. So let's begin with what the hill climbing algorithm is. So it is a type of local search algorithm that focuses on finding the optimal solution by making iteratively small changes, and eventually whether those changes bring us closer to the goal. The algorithm always chooses the neighboring state that seems to be the best based on a heuristic function. But here's the catch. Hill climbing only looks at the current state and its neighbor. It doesn't keep track of where it has been or look too far ahead. This makes it very efficient, but also prone to problems like getting stuck in a local optima where you think you have reached the top of the hill, but you're not at the highest point. In our life, if any one of you have ever climbed a hill or went for hiking, there is a certain point where you think you have reached the peak, but when you reach the peak, it's not the peak, and there is another peak to conquer. Just like that. That's how it works. So we'll focus into two main points. These slides do not contain those points. This slide goes into a more detailed definition of what hill climbing is, but I'll keep it short and simple. So there's one thing called local heuristic search, and there's another thing called global heuristic search. So what is a local heuristic search? This is when the algorithm makes decisions based solely on the current state and its immediate neighbors. Okay, like if you can see at this, looking around and deciding whether to take the steepest step upwards without knowing what's beyond the next point. It's like hiking in a foggy weather where you focus on your neighbor and you just keep taking decisions. And whereas global heuristic search is a broader picture and evaluates multiple steps ahead to avoid getting stuck in a suboptimal peaks. In this case, we apply a more comprehensive evaluation to guide the search in a smarter way. Okay, and I'll show you both examples, uh, covering both local and global heuristic searches, which are applied to solve the problem. So I'll look into my own notes. Let's just abandon these slides for a moment because these look into the more detailed parts of what hill climbing is. Moving on. All right, so let's look at the specific examples from my notes, which solves the problem using the hill climbing algorithm. Like I said, we are gonna talk about local heuristic search and global heuristic search. So we have an initial state on the left side and a goal on the right side. We want to transform the initial state into the goal state using both the local and heuristic search. Let's break it down step by step. First, we apply the local heuristic search, where the initial state is labeled with four entities, which are A, B, C, D. Okay. In the initial state, these values are set to specific numbers. Like, for example, our goal state is to adjust these values to match the goal configuration, where each value is set to plus one, like one, two, three, four. Now, why plus one? Because this shows us the f value, which is 4, which means the goal for us to reach is 4. And these are at the right place. The goal state has every entity at the right position. So if it's in the right position, we add for plus 1. And if it's not, we add for minus 1. Suppose we know A is at the bottom, then B, then C, then D. And here, looking at this, B isn't in the right place. C, D are, because C is above B, D is above C, and A is not in the right position. So for that as well, we'll use -1. The heuristic value f represents how far off we are, like I said. So if A is at 1, I'll repeat again. If A is at +1 but B is at -1, we calculate the overall fitness as f is equal to 0 initially, like I said, and then f is equal to 2 of the first after the first step, like I said, +1 +1 -1 -1 equals to 0. And if we bring 1 down here, then we get +1 for 1 because it's at the right position. So +1 +1 +1 -1 is equal to 2. All right. In the first step, like I said, we check the neighboring state by making small changes. You can see here, like I pointed out, A and B's position. After evaluating each change, we calculate a new f value. If this f is better than the previous f, it means we are moving in the right direction. See, but in this example, after a few moves, we hit a local optimum with f2, and the algorithm can't improve the state further with local moves. This is the classic problem with hill climbing. It gets stuck in a local optima. Like I said, I can bring d here as well, but it goes back to the same value as the initial value, which is f0. So we are stuck at optima position. So that's how we face problems with local heuristic search, and these problems are overcome by global heuristic search. Okay, let's apply the global heuristic search for the same example. Now we know this search looks beyond the immediate neighbors and evaluates the state in a more comprehensive way. It's like zooming out to see the entire landscape instead of just focusing on the next step. Focusing on the next step. Sorry. Now, in this case, we found that the global heuristic search leads to a much better result because looking at the initial state. Now, I'll tell you a point as well. Like when the base of the step, the base of the entity should always begin with 0 and then -1, -2, -3. And these are the initials, which we have as -6, and the goal should be +6. Looking at this, like I said, base is 0, and then we have +1 +2 +3, adding up all we get 6. Now using global heuristic, we have to approach this final goal. Okay, like I said, we first we bring out a out. Okay, now you should always remember that if values are given like these, you cannot just replace two together. You can only move one by one. Okay, and if I put a down here, I can put d up on this, or on the left side, or sorry, on the right side, depends. So let's move on. uh, let's break down the solution. Like I said, we have evaluation of a b c d, or I can say b c d a, and the final goal is this. Okay, sorry. Now we bring down a to the base, which equals to 0 and 0, -1 -2, and after calculating all this we get -3, which is better than the initial. So what happens in global is when a new state is better than the previous state is removed, which makes it more efficient, as it makes it more efficient to work, and it's not heavy to handle. Okay, as the resources are cleared. Now moving on, let's bring d upon a. Okay, if we bring d upon a, like I said, the higher the tower, the more the values, like 0 -1 -2 -3 -4, etc., etc. If I bring d upon a, or even beside a, it doesn't really matter. Actually, it does matter, because we want the goal state to be a b c d, right? Suppose I brought d upon a, which equals to -1 -1, and again we have a better f value than before. So this gets cut out, and we get this. Now looking up into the another picture we have of the continuation, we in the third possibility we brought d down. Like I said, we can bring d to the right side as well, which gets us a better f value. So let's forget the previous value and let's begin with this one, where f is equal to -1. Moving on, we even bring down c to the base, which equals to all 0. This is the new best value, removing the previous one where f is equal to 0. We continue with this. Now now we remember that the goal value is a, b, c, d. So let's bring b upon a. We brought b upon a, which turns into positive 1, like I said, because if it's in the right place, it turns into positive plus 1. So now we have plus 1, right? A, b, d, c. Base as 0, always 0, and then 1 up, so plus 1. We have f1. Now let's bring c upon b. We brought c upon b. Now we have ABC, which equals to 0 plus 1 plus 2, and D as well as, D as always 0. Base should always be 0, remember that. So we got this. Now this equals to f plus 3. Now let's bring D upon C, which gives us the final state, A, B, C, D. 0 plus 1 plus 2 plus 3, that equals to f is equal to plus 6. Hence we have solved this problem, and it was the most easy problem to learn. Of course, our sir taught us this in the class morning. I'll continue the next video. In practice, hill climbing is used in many optimizing problems such as scheduling, pathfinding, and even solving problems like the 8 puzzle, like we did in the previous one, or even traveling salesman problem. However, its tendency to get stuck in a local optimize something to keep in mind. That's where variants like stimulated annihilation or genetic algorithms can help, which are brought up next, not in hill climbing. So that's it for today. Thank you for watching. I hope this breakdown of the hill climbing algorithm gives you a better understanding of how it works and how local and global heuristic play a global role. Play a role. If you have any questions, drop them in the comments below. Don't forget to like and subscribe for more videos on AI and algorithms. See you next time.